Okay, so then I'm happy to introduce the last speaker for today, Edison Lucu-Samon, also from Universidad de los Andes. And he's going to talk about 1D Schrödinger operators with singular interactions on non-discrete sets.
Thank you, Christoph, for the invitation and the opportunity. So, I would like to divide the talk into parts. The first one, a big introduction, where I'm going to talk about the singular interactions. And after that, I would like to talk about the classical Sturm-Liouville theory, because I would like to do a parallelism between the classical Sturm-Liouville theory or some cases. And after that, what happens with the delta interactions. And in the second part, I would like to talk about the operators with the delta interactions. And finally, maybe it's not a part of it all, but it's just one slide with with some open questions or question, because I'm not 100% sure if it's still open, but questions about the future work. So let's start with the single interactions. So we know the Schrödinger equation is the form. It, it calculates the energy states, and it reduces to the study of this differential expression. Please take in account this h, that is the normal differential expression of a Schrödinger operator. If this potential B is locally integrable and real, the things are well studied. We will see, but it's well studied and well known, and the spectral theory about it is super developed and really well known. But in the case, if B is a distribution or if B is a complex potential, the things are more difficult. So now let's move the single interactions. One of the motivation of these interactions are papers like this, the conic penny model. They work the Schrödinger equation with this potential, this B. And of course, they put like some barriers, periodic barriers with length B and height B0. And they do the calculations of the energy states. Doing the same calculation, they tends the B to 0 and the B sub 0 to infinity. And this potential, if we do that, approximate the potential B to a sum of delta interactions. So normally, if you have periodic potential, you know that the spectrum tends to have a band structure or something like that. So they have the conjecture about this delta interaction that maybe give even the how to say it's a periodic potential because it's on the all natural numbers. So they have the conjecture that it could be or should be the same band structure. But we will see that it's not so simple with the delta interactions. So motivated on this kind of papers, we started to study these differential expressions. So in more a general way, if we have x a point of the a point on the real line and some alpha a sequence in the real line, we would like to study this equation. So in the point of view spectral theory, we would like to see what happened with this differential expression. So please note that we have now the differential expression like this. But no. Nah. Yeah, U and H. U with deltas and H normal. Okay. Normal Schrödinger in this way. Non-normal as operator. So, of course, here's question is, it is possible to find a self-adjoint operator for this differential expression. Okay, it's not so simple, but in general way, but some cases, yes. So the thing with the delta interaction is this interaction doesn't act like a classical potential or a classical multiplication operator, because if you try to solve this kind of equation and if you integrate, globally speaking, on the near of the interaction point, and you make then this epsilon to 0, you obtain this condition. So these interactions acts like in the domain, or or say something, yeah, it acts in the domain. And okay, it doesn't destroy maybe the wave function, but destroy the smoothness of the function. So if we move to a specific operator, we know that we can this operator or this possible operator associated to the differential expression can be an operator in all the real line. So we need to remove the points of interaction of the continuity of the H2 or the old H2. So we move to this operator, consider these kind of interactions, and please take into account this dn, the distance between point of interactions, and we consider the following operator. A sub alpha is equal to second derivative, but with the condition of interactions in the domain. So, given a sequence, we have the question if this guy is always self-adjoint, and of course, if we manage to find the self-adjoint operator, what happened with the spectrum? So before to answer this or say all theory or on all works related to this, I would like to talk about first of the classical sum theory. So just recall the for a symmetric operator, we have the deficiency indices is this dimension. Of course, recall that if we have a symmetric operator, it has extensions, self-adjoint extension, if only if the deficiency indices are equal. And especially if we have deficiency indices 0, 0, the operator is essentially self-adjoint. And yeah. So in general way, just to remember what happened with the Schrödinger operator, classical Schrödinger operators, we have this pre-minimal operator, it is used to call in this way. This guy is closable. If we close it, we obtain the minimal operator, as we defined before. And of course, we have three cases. It is really well known that we have these three cases. And here, I would like to focus here. This case 1, 1 is when we have 1 point, maybe on one case when we have 1, 1 is one regular point, regular, and it could be infinity. Okay, when yeah, it's when we have one regular point. It is when we can define the boundary condition of this point, and maybe another point when the solutions of this equation, of the algebraic equation, are not in L2. Now, let's move to something. Yeah, this is remark. So, let's move to this object that is the Teichmar function. In the case then when we are in the case of 1, 1 deficiency indices, so we have a regular point A and another point B. Here we have the limit point case. And if we manage to find a fundamental system with this form, so the Weil function is the function such that this combination, the linear combination, are in L2. And it is a really well-known function. It is used to be called directly to Neumann map, and the eigenvalues of this problem, when we impose this boundary condition, are the poles of the Bell function. So the Bell function, it it works to find the eigenvalues. So in a small example, the classical example, and this or the easiest example is when we have the Laplacian. So recall that these all the self-adjoint extensions. We have the essential spectrum always is zero, the interval 0 to infinity, and the Gimbal equation is super easy to find the fundamental system for this problem. And if we manage to find the fundamental system, so we can calculate explicitly the Weyl function. And of course, this function has no poles, so it means that we don't have eigenvalues for the problem. In the case that for the self-adjoint extension, when alpha is equal to 0 here, so we have the boundary condition f of 0 equal to 0. So something that I would like to focus here is the Weyl function can detect the eigenvalues even in the essential spectrum. So it is something known in these kind of problems that it is usual that the embedded eigenvalues, I mean the eigenvalues in the essential spectrum, used to be really difficult to find because these are really sensitive or are really difficult to even to appear. But the Weyl function is a good tool to calculate it, but it's not the only one. But it's a nice tool to do that. So example 2, compactly supported potential. I mean, this guy, this B, this has compact support on 0 to on this interval. So we have the same case. We have deficiency, and this is 1. We have the same self-adjoint extensions in terms of the domain. Oh, sorry. Here is plus B. And the essential spectrum is the same, but in this case, just putting this potential, the Weyl function is really difficult to calculate. Okay, we can calculate the Weyl function in terms of maybe some asymptotic formulas, but it's maybe really difficult to find the poles of that function because if we use the trick of the asymptotic formulas, the poles are completely not clear. But it is possible to calculate. But it's not easy to find the poles in this case. But if we do, given that this guy is a compact support potential, so we can use the Glasson separation principle, and we can manage to deduce that we don't have eigenvalues in the essential spectrum. Maybe the 0, but okay, maybe the unique. Okay, maybe 0 is not an eigenvalue, but it could be accumulation point of the point spectrum. It could be. So it happens when we add a weak potential in some terms. So speaking, with a weak string of the domain. But if we add a strong potential as the harmonic oscillator, it is well known that, okay, in this case, just to show what happens if we add a strong potential, is this operator is self-adjoint, and it is well known that with this potential, the essential spectrum is completely destroyed, and we just have punctual spectrum. So, taking this in account, I would like to move to the second part of the talk, that is the operators with delta interactions. But just taking account, I work with three potential, like let's say, with the potential, like with potential that doesn't affect the my essential spectrum, and the strong potential that destroy the essential spectrum. So what happened with the delta interactions? So let's start with the easiest case. If we have finite interactions, the A alpha is always alpha joint. The essential spectrum is not, it doesn't change. It could be proved by finite rank perturbations arguments or compact perturbation arguments. The essential spectrum doesn't change. And there's some results that can count what happened with the negative spectrum. Yeah, there are a lot of papers that do that, especially these two. And the picture of the spectrum is something like that. Please note that we still don't have results about the uh, embedded in values. I mean, what happened here with embedded in values? We don't know. Okay, we know, but not here from these results. So let's move to the case of infinite interactions. So we have the bad infinite interaction, but no accumulated even in infinity. It happens again. My operator is always alpha joint, and if the strength of the interactions, just to recall that my interaction are of this form, delta plus x minus xn. This is my potential. This guy are this are the strength. This guy, the alpha n. And if this alpha n is too strong, then this essential spectrum of the Laplacian is completely destroyed. So it happens when we don't have accumulated, when we have a discrete set, infinite set, but discrete. What happens if the points is still discrete, but the points tends to accumulate in sense of the distance tends to 0? We have two cases: the destroyed spectrum if the alphas are small, let's say, this essential spectrum is conserved, and if the alphas are strong, again it destroyed the spectrum, the essential spectrum. So, and finally, the thing that I studied, when we have an accumulation point of these deltas, the classical theory, let's say, it doesn't work to prove that the A sub alpha, the operator with the delta conditions at the domain, the standard theory doesn't work properly to prove that the A alpha is a self-adjoint operator, but using some tool that I will explain in the next slide, Edgar Unterschel could manage to prove that, yeah, it could seen as a self-adjoint operator, and that if the alphas, if the alphas of the interaction are in L1, it means are super small. The essential spectrum is still conserved. I mean, we have the sorry, this is not A. Is in this case is the essential spectrum of Laplace. I mean, 0 to infinity. So of course, it doesn't mean that negative variables couldn't appear here. We could have negative values, either are really difficult to count or calculate, but we don't have so much result about embedded eigenvalues of these interactions. So another question about all these works is what happened with the embedded eigenvalues. So in my PhD thesis, or one of question of my PhD thesis was exactly that. What happened with the embedded eigenvalues of these operators? Or yeah, I mean, but because we have two kind of scenarios. The first one, we have the same essential potential that conserves the essential spectrum and doesn't generate embedded eigenvalues. We have a strong potential that destroys the essential spectrum, but the middle point should be that some potential that generates embedded eigenvalues. So this is a natural question, but really it's difficult to do because even in the normal case, I mean, when B is a locally integrable function, uh, there are other works, but these works are what to say? We don't use they don't use the normal theory. It's very specific in each case. So I focus it in this case when we have a point when we have an accumulation point of the interactions. And um, before to say what happened with this case, I would like to describe the tool that I use in this paper, their presentation. They practically they consider this differential expression, and of course, in this differential expression, it is contained all classical theory and even the singular theory, in which terms that with this differential expression, if we define the quasi-derivative here, um, it means the derivative with respect to mu, we can put the delta interactions here in the differential expression. So with these two, and they develop all the theory, all Sturm Liouville theory with these measure coefficient values. And if we put the delta measures in this guy, in this chi, we obtain the conditions of the delta interactions, as you can see. So they developed all the classical Sturm Liouville theory. So for the case of the I mean, for this differential expression tau, it happens the same that in the normal case, the classical case, we have deficiency, and this is 0, 0, 1, 1, and 2, 2. It depends of the measures. But in the case of 1, 1, there exists again the Weyl function. So with this tool, we say with my advisor, so if we would like to answer the question of the embedded values, maybe the Weyl function in this case is a good tool to do that. And yes, so if we resync the interactions or the domain just to the positive reals, we managed to prove that in this case we are in the regular case at 0 and in the limit point case at infinity, and we can calculate the fundamental system. Please note that here is inside the fundamental system of the Laplacian. So we managed to calculate this, and actually it's a funny calculation because after some details of convergence of the Laplace transform, you can do that as exercise of differential equation course. And it's a funny calculation. And if we have the fundamental system, so we managed to calculate the Weyl function. So we are able to calculate the poles of this Weyl function, and we have a formula of the poles. That is when this guy is equal to 0. But this story is not completely, it's not it's not completely happy because we managed to calculate explicitly that for these two cases, we don't have embedded any values. And in the case for more interactions, the value function is not it's not a good idea to do that. But with class separation principal argument, as in the case of a compact support potential, we can manage to prove that. It's the same idea. The things works completely equal in the classical case, thanks to the currential approach. And finally, I would like to do some questions. 3 questions. What happened with the absolute and singular continuous spectrum? I think that is a deep study of the value function. What happened with the strong interactions? We lose the self-adjoint, but we conserve the symmetry. We conserve the symmetry of this operator, and which conditions should have x and alpha for generate embedded values, because until now we don't have the middle point. And yeah, it's all. This is my principal reference, my thesis. And of course, the big articles where I was motivated. I have a lot of bibliography more, but this is the principle. And muchas gracias.
Thank you so much.